Picture your kitchen counter. A bottle of olive oil, a splash of red wine vinegar. You pour them into the same glass and stir hard. For a moment they look unified. Then you stop, and within 30 seconds, the two liquids pull apart. A visible line forms between them like a border you cannot erase. You have seen this 100 times. It seems like a small kitchen irritation. But the same physical law operating in that glass is also drawing visible ocean boundaries across the open sea lines you can see from a boat deck, lines that shape the climate of entire continents. The question isn't why those lines form. The question is what happens to all of us when they begin to shift. Subscribe now or lose the thread. The algorithm buries this kind of content. Pin it down. By the end of this video, you will understand exactly why the Gulf of Alaska displays one of the most dramatic, visible ocean boundaries on Earth, what the physics of salt and temperature have to do with European winters, and why the line visible from the surface is only the beginning of the story. Here is what the viral version gets wrong. The famous photographs, labeled "Where Oceans Meet and Never Mix," almost never show to oceans. The real science, the actual physics behind why oceans don't mix, is stranger and more consequential than any caption. Ocean mysteries, this deep, require more than a photograph. We will move through 5 geographic locations: the Gulf of Alaska, Cape Horn, the Strait of Gibraltar, Cape Agulhas, and the deep Atlantic floor, each one adding a layer to the same underlying marine physics: the halocline, the thermocline, the invisible architecture beneath every line you have ever seen. This journey begins with the image you've already seen, and almost certainly misunderstood. The photograph has circulated online for years. A line running through open water, dark blue on one side, bright turquoise on the other. The two colors so distinct, they look like someone drew a border with a ruler. The caption usually says something like, "The point where two oceans meet and never mix." Millions of people have shared it. The image is real. The line exists. But almost everything the caption claims about it is wrong. The most widely shared version was taken during a research cruise in the Gulf of Alaska in 2010. When you track down the original documentation, not the viral caption, but the actual scientific context, you find something immediately interesting. The image does not show to oceans meeting. It shows two bodies of the same ocean meeting, two regions of the North Pacific with dramatically different densities, different temperatures, and different histories, running alongside each other like parallel rivers that refuse to share a bed. Why refuse? Consider what water actually is at the physical level. A cup of seawater is heavier than a cup of fresh water. A cup of cold seawater is heavier than a cup of warm seawater. This isn't subtle. The difference in weight between highly saline ocean water and nearly fresh glacial meltwater can be as significant as the difference between water and light cooking oil. When you combine two liquids of markedly different densities, the interface resists mixing, not because of any mysterious force, but because the denser liquid wants to stay below the lighter one. Disrupting that arrangement requires continuous energy input. Without it, the boundary reasserts itself. Now scale that up to the Pacific. The line in that photograph is the edge of a glacial meltwater plume. Cold, fresh, mineral-rich water pouring off the glaciers of the Alaska Range and meeting the older, saltier, warmer water of the open Pacific. The contrast in color comes partly from minerals. Glaciers grind rock to a powder so fine it is called glacial flour. Particles small enough to remain suspended in water almost indefinitely, scattering light at a wavelength that produces the distinctive turquoise-green color. The open Pacific carries no such sediment. Its deep blue comes from depth and clarity. So the line is real. The physics is real. The spectacle is entirely genuine. But the story it tells is not two oceans that never mix. The story is, water carries its history in its density. And that history creates visible structure at planetary scale. The irony here is that the viral version undersells the reality. A glacial melt plume running alongside open Pacific water already represents thousands of years of compression, grinding, and slow dissolution into the sea, all of it visible as a color shift from a research vessel. but that is a local boundary. A regional story. If a single watershed can produce a line you can see from a boat, what happens at the places where two genuinely different ocean systems, with different temperatures, different salinities, and different histories measured in centuries actually collide? For that answer, we have to go to the most photographed ocean boundary on Earth. The Gulf of Alaska sits at the top of the Pacific, cupped between the Alaska Peninsula to the west and the Alexander Archipelago to the east. On a clear day from altitude, the water isn't one color. It isn't even two colors blending gradually into each other. It is two distinct bodies of water running alongside each other in sharp contrast. The boundary between them tight enough that a research vessel can have its bow sitting in green water while its stern sits in blue. This boundary is not fixed. It shifts with seasons, with currents, with the rate of glacial melt, but it persists. Year after year, the same general line reasserts itself in approximately the same location. Why? The answer begins in the mountains. The glaciers of the Alaska Range and the coast mountains are grinding. Millions of tons of rock crushed by the weight of ice moving centimeters per day. The output of that process is glacial flour, rock reduced to particles between 1 and 100 micrometers in diameter. To put that in scale, a human hair is roughly 70 micrometers wide. Glacial flour particles are small enough to remain suspended in meltwater for weeks, coloring it a milky green-gray that photographs often render as turquoise. When this meltwater drains into the Gulf through rivers and direct glacial runoff, it carries not just color, but a fundamentally different density profile than the open Pacific water it is entering. Fresh glacial meltwater is colder and less saline than the open ocean. Less saline means lighter, less dense. The open Pacific water in the Gulf has been circulating far longer, carrying decades of evaporation history, biological activity, and accumulated salt. The density difference isn't dramatic by the standards of oil and vinegar. It's a matter of grams per liter, not pounds per cup. But at oceanic scales, grams per liter is enormous. It's enough to maintain a stable halocline, a zone where salinity, and therefore density, changes rapidly with depth, that actively resists the mixing you would expect from wind and waves. This is the counterintuitive part. You would expect surface turbulence to obliterate any boundary between adjacent water masses. And eventually it does. But eventually, at oceanic scale, can mean weeks, months, even years. A halocline doesn't behave like a wall. It behaves like a gyroscope. The harder you push it, the more it pushes back. The consequences for marine life are profound. The boundary zone between glacial meltwater and open Pacific creates a nutrient trap, cold. Mineral-rich freshwater, meeting warmer, biologically active saltwater generates explosive concentrations of phytoplankton. These microscopic organisms are the base of the marine food chain. Their blooms at the boundaries support some of the richest fisheries on Earth, millions of seabirds, dozens of whale species, salmon runs, and a commercial fishing industry worth billions of dollars annually. And here is what the viral photographs almost never mention. This boundary is moving. As glacial melt accelerates, the freshwater input into the Gulf of Alaska is increasing. The zones where these water masses meet are changing location, changing chemistry, changing the distribution of nutrients that the entire ecosystem depends on. Scientists have tracked this shift for decades. The line that looks so stable from a research vessel is at the timescales that matter for climate, already in motion. If the Gulf of Alaska boundary is this consequential, what happens when two entirely separate ocean basins, with their own distinct chemical histories, are forced through the same narrow corridor with nowhere to escape? For that, we go south, to the bottom of the world. Most people who have studied the age of sail remember Cape Horn as the graveyard of ships. More than 800 documented wrecks in the waters around the southern tip of South America, with uncounted losses before official record-keeping began. The standard explanation focuses on wind, the roaring 40s and screaming 50s, the unobstructed bands of latitude, where westerly winds circle the globe without any landmass to slow them down, building waves that 19th century sailors measured in stories rather than meters. The wind explanation is correct. It is also incomplete. The Drake Passage, the 600-mile gap between Cape Horn and the Antarctic Peninsula, is where the Atlantic Ocean and the Pacific Ocean meet. Not the way a river meets the sea. Not the way a glacial plume meets open water. These are two ocean basins with fundamentally different chemical and physical histories, forced through a relatively narrow corridor by the geometry of the planet. The Atlantic is, on average, saltier than the Pacific. The reasons involve the geometry of the Atlantic basin, the pattern of evaporation over its surface, and millions of years of differential circulation history. The result is measurable. Atlantic water entering the Drake Passage from the east carries a different density signature than Pacific water pushing in from the west. When water masses of different densities meet at speed, the interface between them becomes turbulent in 3 dimensions, not just at the surface, where waves are visible, but at depth, where density layering creates shear forces that modern submarines navigate with care. Consider the navigational consequence that almost no popular account mentions sonar systems bounce sound waves off the ocean floor to measure depth and detect obstacles. Sound travels through water at a speed that depends, critically, on the density of the water it is crossing. When a sonar beam crosses the boundary between 2 water masses of significantly different densities, a sharp halocline or thermocline, the beam refracts exactly the way light bends passing from air into glass. The return signal arrives from the wrong direction, or not at all. Navigators in the Drake Passage have reported what they call phantom bottoms, false depth readings generated not by the seafloor, but by the acoustic shadow cast by a density boundary. The same interface that produces the color line in the Gulf of Alaska is in the Drake Passage, producing acoustic mirages that can make a ship believe it has 200 meters of clearance when the actual seafloor is far closer. This is not historical. Modern vessels still navigate this corridor. The density boundaries are still there. And what current oceanographic research adds to this picture is significant. The chemical difference between Atlantic and Pacific water in the Drake Passage is detectable not just in salinity readings, but in carbon dioxide concentration, pH, and the distribution of trace minerals that biological communities on both sides have been adapted to for millennia. The Drake Passage isn't just where 2 oceans touch. It is where planetary scale chemical systems exchange matter at a rate that influences atmospheric composition on geological timescales. The passage processes roughly 130 million cubic meters of water per second. Every river on Earth combined delivers approximately 1 million cubic meters per second to the ocean. The Drake Passage alone moves 130 times that volume every second. And within that flow, the boundary between Atlantic and Pacific water is conducting a continuous chemical exchange that has no marker on any navigation chart and no caption on any photograph. But the most unsettling part is still ahead. If what you just learned bothered you, good. That means you're paying attention. Subscribe so you don't miss what comes next. Because what we're investigating in the next video makes this look like the introduction. The Strait of Gibraltar is 9 miles wide at its narrowest point. To stand on the Spanish coast and look south at the Moroccan shore, you would not guess that the water moving through that gap is doing something with no simple analogy in ordinary experience. It is moving in 2 directions simultaneously, not back and forth on a tidal schedule, but both directions at once. 2 currents, one above the other, flowing in opposite directions at the same moment. The Atlantic side of the strait carries lower salinity and lower density than the Mediterranean side. The Mediterranean is a nearly enclosed sea in a hot, dry climate where high evaporation rates have concentrated its salt over millennia. Mediterranean water is measurably denser than Atlantic water. Physics makes the decision that geography cannot avoid. Lighter Atlantic water flows in along the surface. Denser Mediterranean water flows out along the bottom. A 2-story exchange, continuous. It has been running for roughly 5.5 million years. Since the last time the strait was sealed and the Mediterranean dried into a vast salt flat, a geological event called the Messinian salinity crisis that makes the story of the Gulf of Alaska seem recent by comparison. During the Second World War, German submarine commanders discovered that they could navigate through the Strait of Gibraltar without running their engines. They would ride the outflowing Mediterranean undercurrent westward, silent, invisible to Allied sonar, batteries fully charged. The density boundary that generates the two-story flow also generated the acoustic shadow that concealed them. Ocean physics, unchanged for millions of years, became a tactical instrument of war. Cape Agulhas, at the southern tip of Africa, is the only place on Earth where two fully formed ocean basins, the Indian and the Atlantic, meet in open water without a constraining channel. The Agulhas current sweeps warm Indian Ocean water southward along the African coast, and then, at the Cape, turns generating enormous rotating columns of warm water, called Agulhas rings, up to 200 kilometers in diameter, that break off and drift westward into the South Atlantic. Some reach the coast of Brazil. Some influence tropical storm formation in the Atlantic basin. Sailors describe crossing the Agulhas boundary and feeling the temperature difference at the surface warm. Indian Ocean water giving way to cold Atlantic water within a few boat lengths. These rings are not a curiosity. They are part of the mechanism that keeps the Atlantic's overturning circulation functioning. And that circulation is what moves warm water north toward Europe. Recent monitoring data shows the Agulhas ring system is already changing, and scientists who model European climate watch it accordingly. Everything visible on the surface is driven by physics operating silently beneath. The word halocline comes from the Greek halos, salt, and clinine, to incline. It describes a zone in the water column where salinity and therefore density changes rapidly with depth. The thermocline is its thermal equivalent, a zone where temperature drops sharply over a short vertical distance. Together, these two structures govern the density layering of the ocean in ways that make the surface boundaries we have examined look like rough approximations. A single drop of seawater carries two variables that determine where it belongs in the water column: its temperature and its salinity. Cold water is denser than warm water. Saltier water is denser than fresher water. Combine these variables and you arrive at a specific density value that determines exactly where that drop will settle. It sinks until it finds water of equal density, then spreads horizontally. It will not continue downward into denser water, and it will not rise into lighter water. The ocean, in this sense, is not a uniform liquid. It is a series of stacked layers, each resistant to mixing with the layers adjacent to it. The haloclines and thermoclines we have examined at the Gulf of Alaska, the Drake Passage, Gibraltar, and Cape Agulhas, are the extreme versions of structures that exist everywhere in the ocean. Global architecture that has been in place for millions of years. What makes these locations remarkable is not that the physics is unusual. It is that the contrast is great enough to become visible. Here is where the story expands from geography to planetary systems. The same density layering that creates visible color lines and sonar. Anomalies and two-story currents at Gibraltar is the engine of the global thermoline circulation. The system oceanographers call the ocean conveyor belt. Cold, dense, salty water in the North Atlantic and around Antarctica sinks to the ocean floor and moves slowly toward the equator. Warmer, lighter water moves along the surface to replace it. This circulation distributes heat, oxygen, nutrients, and dissolved gases around the planet on a timescale of approximately 1,000 years. It keeps northern Europe significantly warmer than its latitude would otherwise permit. Without it, winters in London would more closely resemble winters in Labrador. The density boundaries we have been examining are not isolated curiosities. They are the surface expression of this system, and that system is showing measurable signs of change. The AMOC, the Atlantic Meridional Overturning Circulation, has weakened over the past century. According to peer-reviewed reconstructions published in 2021 and confirmed by subsequent monitoring, the lines that look so stable from a research vessel are at the timescales that climate operates on, in motion. Science has not settled what the full consequences will be, but the leading hypothesis points toward disrupted rainfall patterns, altered storm tracks, and significant changes to the agricultural and fishery zones that billions of people depend on. What we have found, moving from a kitchen counter through 5 of the planet's most consequential geographic locations, is this: the ocean is not a unified body of water. It is a collection of distinct water masses, each with its own temperature, salinity, density, and biological character, held in structured arrangement by physical laws that have been operating continuously for millions of years. The visible lines at the surface are not exceptions to the system. They are the system, made briefly visible. And here is what that reveals about us. We have spent 2 centuries building a civilization calibrated to a climate that depends on the stability of these density boundaries. The warmth of European winters, the reliability of Atlantic storm patterns, the productivity of fisheries from Alaska to South Africa. All of it is downstream of the same physics that keeps olive oil from dissolving into vinegar. We have been living inside a system we only recently learned to read. Imagine standing at the bow of a vessel in the Gulf of Alaska. The line runs alongside you, dark blue on your left, green-gray to your right. It has no fence, no warning sign, no name on any chart the crew is using. It is simply there. A product of physics and time, quiet and consequential, and entirely indifferent to whether we understand it. The ocean keeps its boundaries. The question is whether we keep ours.